Hello everyone, I hope you are doing well. In this video, we'll be talking about operators in quantum mechanics. We can summarize this whole video. Here we can see the position operators. Okay, X operator, Y operator, Z operator, R operator. In 3D, we can write it like that. Momentum operator, X, Y, and Z representation. And then in 3D, we saw that it is equals to this, where del is equals to this. Okay, in Hamiltonian operator, we saw that it is equals to this term. Okay, we can put hat over the potential energy term as well because it's operator basically. So in 3D we have this situation. This is the 1D case where we use the x dimension only, partial square by partial x square. In 3D we use the del operator form, or you can use the p form as well. So it's actually equals to kinetic energy term plus the potential energy term. This is the kinetic energy term. We have p square where p is the momentum operator. So in 3D we can put the momentum operator in 3D part. Okay, and doing so it becomes minus h square by 2m del square plus v, and that is it. This is the Hamiltonian operator in 1D. This is the Hamiltonian operator in 3D. Moving on, using the Hamiltonian, we saw that this is the Schrodinger's equation. Okay, we wrote the position dependent form. Let me write the time dependent form, which was iota h cut partial by partial t. Since we can see that both of these are Hamiltonian, so they must be equal to each other. Okay, so that is what we did here. We also used wave function. We applied the wave function on the right hand side. Okay, so additionally we wrote the wave function here. So this is the time dependent form, and we can write it like that. In place of h in here, we can write the position dependent formula in here. I use the 1D forms. You can use del square in place of this thing to convert it into a 3D case. Okay, that's really simple. Just use r in place of x in there here, and in here you can use del square simply. For time case you don't need to change anything, and that is the time dependent form Schrodinger's equation. That is the time dependent form of Schrodinger's equation. You should know it because it's the basic one, and using some assumption we can derive the time independent form, and we derived it. You saw that we got this form, and in h we have the potential energy term that is independent of time. There is no time involved in here, we can see in the whole equation. So this is the time independent form. You can easily remember it from this equation. Okay, you just need to remember what is h equals to. H is equals to this. You just have to remove the time t here, and rest of everything is the same. Okay, you can easily remember this form because it's really important. I think that much detail is enough for this video, and we'll be seeing the application of all these operators and these forms in later videos. And if you have any queries, if you want me to add more details into this video, let me know. I'll do that. And till then, take care and goodbye. Here, besides the all these details, we can write the time dependent wave function as well, minus iota e t by h cut.